after we have obtained some basic understanding about the internal workings of a neural network, let's try to build a neural network to recognize handwritten digits from the MNIST dataset. The MNIST dataset has a training set of 60,000 examples and a test set of 10,000 examples. The entire dataset can be downloaded from this particular website, and so the input to our neural network will be these grayscale images of handwritten digits, and each image has been normalized to a grayscale value ranging from 0 to 255. So 0 means black, and 255 means white. And each image, this kind of square image, each image has 28 by 28 pixels. So in a computer program, each image is actually represented by a matrix with 28 rows and 28 columns. And the elements inside of this matrix have values between 0 and 255. So the smallest value inside the matrix is 0, and the biggest value inside the matrix, the biggest possible value inside the matrix is 255. Sometimes it's sort of less than 255 because those whites are not really exactly whites. They have some grays in them. And the ground truth for each input image is a number between 0 and 9. So the ground truth for this particular image is going to be 6. The ground truth for this image is going to be 1. And the ground truth for this image is going to be 9. For this is a 4, 2, 5. Right? So in this MNIST dataset, this kind of ground truth is called the label for each input image. So the label for this image is going to be 6. And then the label for this image is going to be 1. The label for this image is going to be 8. The label for this image is going to be 7. It's just like that. So in our neural network, in our computer program, how do we actually represent each label, right? We can certainly just use the integer as the label, just one integer, right? But in practice, when we actually try to solve this problem using neural networks, we are actually represent each label. We're actually representing each label using a vector with 10 elements. So if the label has a value of 6, which means that the input image is actually a handwritten digit of 6, then the 6th element of the vector is going to have a value of 1, and the other 9 elements inside of this vector all have value of 0. And this kind of a representation of the label is called one-hot encoding. One-hot means that you have only one element of this 10-element vector that has a value of 1, and every other elements are just zeros. Right? So that's called a one-hot encoding. And we denote the elements of this one-hot encoding vector as T, representing the ground truth, basically. Right? So for this particular input image, the ground truth is going to be this particular vector, with the 6th element being 1, and the zeros first, second, and then every other elements of this encoding vector is going to be 0. Right? And then for the second input image, it's going to be 1, right? So the one-hot encoding vector is going to have a value of 1 for the first element. This element is going to have a value of 1, and every other element is going to have a value of 0, right? And for this particular image, then it's gonna be the label is supposed to be 0, right? So the 0th element of this one-hot encoding vector is gonna have a value of 1, and every other elements are gonna have a value of 0. So this is called one-hot encoding. So we can basically think of the elements, the value of the elements inside of this vector as probabilities. So for this particular example, the probability that the first image, this image, is the number 6, is a handwritten 6, is 1. And the probability that it is another number is 0. Right? That's sort of the one-hot encoding of the actual label. The output of our neural network will also be a vector of 10 elements. So here I'm denoting it as P0 to P10. That's going to be the output of our neural network. It's gonna be a vector of 10 elements, right? And with the value of each element, indicating the probability of the image of the handwritten digit being the index of that element. So P3 is gonna be the probability that the handwritten image is the number 3, right? And then P6 is gonna be the probability that this input image is actually a handwritten 6, right? So all those black sticks are gonna be the ground truth, right? That's the one-hot encoding of that label, that ground truth label, right? And then all the red sticks are gonna be the neural network predictions, the predictions made by our neural network. So it is actually unlikely that our neural network will be able to recognize digits with 100% confidence. So using a probability distribution over the 10 possible digits can give us a better idea about how confident we are in our prediction. For example, for this particular prediction, even though the digits, the probability of 6 is sort of the largest, right? But it's not really that much larger, for example, than 2 or than 9, right? So in this case, the prediction is not really that confident. We can actually, just by looking at the heights of the different sticks, then we can tell that it's not really that confident. But on the other hand, if the red stick at position 6 is a lot higher, suppose at this kind of position, and then every other sticks are a lot lower, right? A lot lower than this red stick, then we can say that the confidence of our model prediction or neural network prediction is actually quite high. So so using this kind of a probability distribution can give us some idea about how confident we are in our predictions. So our neural network will have a top output layer with exactly 10 neurons. With this exactly 10 neurons. So capital L means that it's the top layer now, right? Capital L. And then the neural index goes from 0 to 1 to 2 and then up to 9, right? So it's exactly 10 neurons. And each neuron's output, the Y capital LJ, right? J goes from 0 to 9, will correspond to the probability of the predicted probability, the neural network predicted probability of the jth digit being the actual handwritten digit. And because each digit is actually mutually exclusive, right? So if it is a number 1, it cannot be a number 9, right? If it is a number 9, it cannot be a number 6. So it's mutually exclusive. And the 9 digits have actually covered all possibilities. There's no, the 10 digits have covered all possibilities, right? We can only have like from 0 to 9. There's no other digits that's kind of available to us. So all the 10 digits have covered all possibilities. Which means what? Which means the summation of the 10 probabilities must equal to 1. Right? The probability of being 0 plus the probability of being 1 plus the probability of being 9, and every probability summed together must equal to 1. So which means what? Which means because Pj equals to Yjl, which means the summation of all the neuron outputs Y capital Lj for the top layer must equal to 1. And this is achieved by using this special output layer. And this output is called a softmax output layer. So unlike in other kinds of layers, the output of a neuron in a softmax layer actually depends upon the outputs of all the other neurons in the same layer. Right? And this is because we require the sum of all the outputs to be equal to 1. So if the logit of the neuron, of the output neuron, is given by Z capital Lj, we can achieve this kind of effect by setting the output Yjl equals to this particular expression. Right? So Ylj equals to the exponential of Zlj. Basically, we are taking the exponential of the logit of the jth neuron, and then we divide it by the summation of the exponentials of all the logits, all the exponentials of the logits in the output layer, right? So this is the index of I goes from 0 to 9. Basically, we are summing up the exponentials of the logits of all the 10 output neurons. Right? And the Yjl equals to exponential Zjl divided by this summation. And you can check if you actually add up all the Yljs for the output layer, then you get exactly 1. Right? So by computing the output for the softmax output layer using this particular expression, we can achieve this particular effect. Right? And don't forget, all the probabilities must be larger than 0, larger than or equal to 0, right? And the exponential of the logit could be positive or negative, right? But the exponential of this logit is always positive. Right? So Ylj can indeed be interpreted as a probability because it's always larger than 0. Right? Because this exponential function actually made sure that the Ylj is always going to be positive or being 0, right? And this summation over all the j's equals to 1. Right? So Ylj is indeed can be interpreted as a probability. So a strong prediction would have a single entry in the outputs that's close to 1, and all the remaining outputs would have a value that's close to 0. And a weak prediction would have multiple outputs that are more or less equally likely, have about the same kind of value, right? So that's going to be our output of our neural network. It's called a softmax output layer. And then once we have the output, we need to actually quantify the neural network's output with the ground truth, right? Our ground truth is actually the one-hot encoding, the T's, right? So we have a vector with 10 t's inside of it. T goes from T0 to like T9. Right? That's all our t's. That's the one-hot encoding of the label of that particular image. Right? It also has like 10 numbers inside of this particular vector. So how do we actually quantify the difference between our output probability defined by the 10 y's and the one-hot encoding of the label defined by the 10 t's, right? A vector of 10 t's. So we're going to use something that's called a cross-entropy loss. This cross-entropy loss is a concept from the information theory, right? So how do we actually compute the cross-entropy loss, right? So first we're gonna take the natural log. We're gonna take the natural log of the jth output, and then we're gonna multiply it with the corresponding element inside of our one-hot encoding vector of the label. And then we're going to do a summation over j, over all 10 elements. And then this summation is going to be multiplied with minus 1. So what's going to be the cross-entropy loss is going to look like for one particular input image, right? First of all, the natural log is actually a monotonic function. So small yj will correspond to small log yj, right? So this log is going to be small for small yj, and it's going to be large for large yj. It's a monotonic function, right? So, and then second, if there is a significant mismatch between the output vector and the one-hot encoding, right? So if the output vector has maxima at locations that's kind of very different from the maxima that's inside of the one-hot encoding, then this kind of a multiplication, this kind of component-wise multiplication, right? And then the summation is going to give you a small value, right? It's going to give you a small value. And then take the minus sign of that small value is going to give you a big number, right? You can imagine that suppose the red sticks and the black sticks are kind of a sort of completely inconsistent with each other, are completely uncorrelated. The red stick is the highest at this location, and every other locations are like close to 0. Then a component-wise multiplication is gonna produce a vector that's close to 0, and doing a summation of all those vectors together, all those numbers, component-wise multiplication products together is gonna give you something that's kind of small, right? And because you are also taking the log here, right? So a small, so all the y Lj are gonna be smaller than 1. Right, because it's a probability, the summation is equal to 1, and every number is positive, so every y Lj is going to be smaller than 1. A natural log of some number that's smaller than 1 is going to be a negative number, right? So it's going to be a negative number, right? If that negative number corresponds to is sort of completely uncorrelated with Tj, then this kind of component-wise multiplication and summation is going to produce a very negative number. And then put the minus sign on that very negative number is going to give you a very positive number. Right? On the other hand, if the output vector is sort of very consistent with the one-hot encoding, right? It's very consistent. Then this cross-entropy, you can verify that this cross-entropy, this E, will be close to 0. Right? And this cross-entropy loss is actually used quite often. It's actually used quite often in the so-called logistical regression. It's basically a classification problem. Right? And we'll sort of look into this particular error function in more details in later videos.